Hello students, in this video we will solve one example using Euler's theorem. So we have to solve this differential equation dy by dx is equal to x plus y at x is equal to 1, where y at x is equal to 0 is given as 1. So we will solve this example using by taking different values of h, so that you will understand how values of how when we change values of h, how the final answer changes. Then we will solve this example using analytical method also. So we'll see, we'll check these answers that we have got by taking different values of h with actual answer, and at the end we will see one Python program, and there we'll solve this for other values of h, for very small values of h, where number of observations are very large, number of iterations are very large. For example, there may be 100 or 1000 iterations required, but within seconds uh, we get that answer. So basically these methods are very useful when we implement them in so when we write code on them, okay, or when we use them computationally, then these methods are very useful. So let's solve this. So this is our f of xy, x plus y, x naught is equal to 0 and y naught is equal to 1. Okay, so let us take h is equal to 1 by 2, that is 0.5. So in 2 iterations we will get answer for x is equal to 1. Alright, so this is by Euler's method. Yi is equal to yi minus 1 plus h into f evaluated at xi minus 1 comma yi minus 1. Alright, so here y1 will be, that is y at x is equal to 0.5 will be, so y naught, that is 1 plus h, which is 1 by 2 into f at 0 comma 1. See, x naught is 0 and y naught is 1. So which you can see it is 1.5. That means value of y at x is equal to 0.5 is 1.5. Now one more iteration. So y2, that is y at x is equal to 1 will be, so y1 which is 1.5. Now see here I is equal to 2. So it is y1, that is 1.5 plus h times, that is 1 by 2 times f of f evaluated at x1 y1, that is 0.5 comma 1.5, which is equal to 2.5. So we got answer y at x is equal to 1 is 2.5. Now this is for when we take h is equal to 0.5. Now let us change this value of h. Okay, let us take h is equal to 0.25. Now here we need to perform 4 iterations and then we will get value of y at x is equal to 1. But as this value of h is smaller than this value, so we'll get more approximate answer. Let's solve it. So y1, that is y at x is equal to 0.25 will be, so 1, that is y naught, plus 1 by 4, that is h into f evaluated at x naught y naught, which is 1.25. Okay, now y2, that means y evaluated at 0.5 will be y1, which is 1 upon 1.25 plus h into f evaluated at x1 y1, that is 0.25. Now x1 will be 0.25, you get here, plus 1 comma 1.25. So which you can check, it is 1.625. All right, now you can see here there is a change. When we took h is equal to 0.5, at that time y at x is equal to 0.5 is 1.5, but now it is 1.625. So there is a change. So when we change h, corresponding values also changes. Now let's go for the next iteration, y3, that is when y at x is equal to 0.75, so which will be y2 plus h into f evaluated at x2 y2, so which is 2.15625. All right, next we will find y4, which is y at x is equal to 1 will be y3 plus h into f evaluated at x3 y3, and it is equal to 2.8828125. So this is our answer when we take h is equal to 0.25. Now you can see clearly there is a very much difference. It is 2.5 here and it is 2.88 here. So as h changes, the value changes. Now let us compare these answers with the exact answer. So we will solve this by using analytic method. So dy by dx equal to x plus y. Now this can be written as dy by dx minus y is equal to x. So auxiliary equation will be m minus 1, very simple. Or you can solve this by using, so this is a very simple differential equation. You can solve it by using linear differential equation also, or by converting this to variable separable form, or maybe by using other methods. So now, so here this will give us yc as c1 into e raised to x, and yp as 1 upon d minus 1 operates on x. So this is by general formula. After integration, we will get y as c1 into e raised to x minus x minus 1. Alright, so this is sorry, this is y. Now using initial condition here, at x is equal to 0, y is equal to 1, we will find value of c1, which gives us c1 is equal to 2, and therefore particular solution will be this: y is equal to 2 into e raised to x minus 1. So this is what the solution of this differential equation with this given initial condition. Now let's evaluate y at x is equal to 1. So when you put x is equal to 1 here, it is 2e minus 1 minus 1, that is 3.436563657, because this e is irrational number, so these numbers will continue. All right, so this is what y at x is equal to 1. Now you can see here, obviously the difference is very large, but you can see when we take h is equal to 0.25, we get more accurate answer compared to this one when we take h is equal to 0.5. So this is how, if you take values of h very small, it will give you good approximate solution. Right now these values, comparatively these values are not small, because see here we use only 2 iterations. In the second case we use only 4 iterations. Okay, but if you further reduce this value, if you take values of h very small, then we will get more approximate answer, very good solution, which is almost equal to this. So for that, now we will use one Python program, and there we'll see how this how by changing values of h we can get very good approximation. So we have this Python program here. First we will write our function, which is x plus y, dy by dx is x plus y. Then we will input the initial condition, x naught is equal to 0, and at x naught is equal to 0, y naught is 1. All right, and we have to find for 1. Okay, so xn is equal to 1. All right, now here we will put values of h. Now see, when we put value of h is equal to 0.5, we already know the answer. Okay, it takes two iterations and gives us this answer, 2.5. Then let us change this value of h. Now let us put value of h as second one was 0.25. all right, so check with this value, see what we get here. All right, we are getting the same answer, 2.8828125, but it is not good approximation, right? There is a very much difference, almost 0.6. Let's change this value. Suppose we take value of h as 0. Let's say 1. See what happens. Now there will be 10 iterations, and see we got answer as 3.187, which is comparatively, which is very good, right? Because actual answer is 3.4 something. Now we are getting 3.187. That is only for 10 iterations. So see how by changing value of h we can get good answer or good approximation. Let's further change this value of h to 0.001. In this case there will be, I guess, 1000 iterations, but this will give you answer within seconds. See, number of iterations thousands, and the answer is 3.4338, which is very good answer. Okay, so this is how by changing value of h we can get a very good approximation for h is equal to 0.0001. Okay, there are 10,000 iterations, but look at the answer now. It is 3.43629, which is almost equal to the answer that we got by using analytic method, right? So we got answer correct up to 3 decimal places. So this is how value of h matters. If you reduce the value of h, you will get more approximate answer.